All right, we're on curve sketching part 3. So still under B1. So far we did a quick recap of advanced functions and learned about polynomials, rationals, etc. Then in part 2 we went over maximum and minimums. So we can see here on this graph we have a maximum and a minimum. Often these areas are called local maxes and minimums because they're not the max of the whole graph, because you can see like it keeps going. So there's going to be a bigger value than that one, but these are kind of like the local max and mins. We also called them extrema, and more importantly, we called them critical points, which they are. And we learned we can find them when we set the derivative of the function equal to 0 and solve for x. We can figure out the location of the max or mins. Okay, so in this video, we're going to learn about concavity and the second derivative. Okay, so the first derivative can give us the locations of the max and mins. The first derivative can also tell us the intervals of increase and decrease. But the second derivative is going to talk to us about concavity, like if it's concave down or if it's concave up, and something called points of inflection. So let's talk about terminology first. So if you were to draw tangent lines on this curve, so if we started drawing tangent lines along at every point on this curve, you can see that our tangent lines are above the function. They're on the top of the graph. Okay, so that right there, if you're drawing tangent lines and all of the tangents are above the curve and the graph is curving downwards like this, we would say that this part of the graph is concave down. So all the tangent lines are on top when we draw them, and the curve is going downwards. And then as soon as you're drawing the tangent lines, as soon as they switch to start going below the curve when you're drawing a tangent line, now we would call that section concave up. Okay, so there's two sections on this graph. There's a concave down area and a concave up area. So right in between, right at that spot where it goes from concave down to concave up, there's this point where they switch. When it goes to concave down to concave up, there's this point right there where they switch from the tangent line being on the top to the bottom. And this special point right there is called a point of inflection. And that's where the graph changes from being concave down to concave up, or vice versa, concave up to concave down. There can be multiple points of inflection on your curve, or just one. And we're going to use the second derivative to find out the location of those points of inflection. Okay, so I'm just going to summarize it in this section right here. So, P.S. before we start, you know how we've been doing like the derivative? So that's actually called the first derivative. You can actually keep going, and you can actually find the second derivative called like f double prime of x, and that's the second derivative. So I don't think we've really done that much, but we're going to do it now. So the second derivative can tell us stuff about concavity and points of inflection. So if the derivative equals 0, so if the first derivative is 0, we know that we're at a max or a min. If the second derivative is greater than 0, then we know that the function is actually concave up. So, for example, at this point right here, we would know that the derivative of this function is equal to 0, the first derivative, And we'd also know that the second derivative of this function is going to be greater than 0 at this point, at this local minimum here. And that would tell us that our graph is concave up, and it would also tell us that there is a local minimum here. So we know at a local minimum, our first derivative is 0, and our second derivative will be positive. And it will also tell us that our graph is concave up. Okay, whereas if you have a concave down section and a local max, in this section, we will know that our derivative would be 0, because it's 0 at the max and mins. And our second derivative will be less than 0. And there'll be a local maximum. So that's just a little summary of what happens at the first and second derivative. And then at the point of inflection, so right at the point of inflection, your second derivative is going to be 0. So your second derivative changes from being less than 0 to greater than 0, but right at the point of inflection, it equals 0. Okay, why don't we try one? Okay, so for the function f of x equals x to the power of 4 minus 6x squared minus 5, we're going to find the points of inflection and the intervals of concavity. Okay, so why don't we first, before we even start, why don't we find the first and second derivative? So the first derivative of the function is 4x to the power of 3 minus 12x minus 5. So that's the first derivative. And why don't we also find the second derivative? So the second derivative is found by finding the derivative of the first derivative. So our second derivative will be 12x squared minus 12. Cool, so now we have the first and second derivative. Okay. P.S. Like, you know how derivative is written in this notation? Just for your information, the second derivative would be written like this in the Leibniz notation. You can also write it as y double prime. Okay, so just a notation thing, FYI, just so you know. Okay, so at the point of inflection, the second derivative is equal to 0. So why don't we find that point? Okay, so I'm going to take my second derivative and set it equal to 0. And I'll just solve. Remember, when you take the square root, the answer can be positive or negative. Did I say it? I don't know what I said, but when you take the square root, it can be positive or negative. So it looks like we'll have 2 points of inflection at x equals 1 and x equals negative 1. Okay. So why don't we set up a table like we did in the part 2 video? I think it would be good to set up a little table. So we're going to have x equals negative 1 and x equals positive 1 as our two areas here. And then we're going to need all the spots in between those. So we're also going to need when x is less than negative 1. And we're going to need when x is between negative 1 and 1. And when x is greater than 1. Okay, so those are all of our intervals. And now why don't we test what happens with the second derivative? So just test a value that's less than negative 1 for the first part. So take the second derivative and just test a value. So like, let's just test negative 2 because we know it's less than negative 1. So if we take our second derivative, 12x squared minus 12, and we sub in negative 2, we will get 36. So that is a positive answer. Okay, so we know from up here, if our second derivative is positive, like this, then we have a concave up section. So we know our graph is going to be concave up. then when x equals -1, we know that this is a point of inflection. And if we actually sub -1 back into our original function up here, we would know that that point of inflection is going to occur at -1, -10. Okay, and then let's pick a value in between -1 and 1. I'm going with 0. So let's find the second derivative when x equals 0, and we'll get -12. So that is a negative number. So you know our graph is going to be concave down there. And then at x equals 1, we have another point of inflection. And if I sub that in, it's going to be at 110. Oh, 1 -10, sorry. And then let's sub in a value for when x is greater than, or sorry, when x is less than 1. Oh, just kidding. I think I drew that sign. Oh no, I drew that sign the right way. When x is greater than 1. So let's pick a value like 2. So let's find the second derivative when x equals 2. And we get 36, which is positive. And we know our graph is going to be concave up. Okay, so you can tell the concavity of the graph changes at -1, -10, and 110. So these are the points of inflection. Because remember, points of inflection occur when the graph goes from concave up to concave down, or concave down to concave up. So that's what happens. So our graph's going like this, and then like this, and then like this. So you're getting a point of inflection here and here. What is this, a 4th degree? Yeah. So that makes sense. We have 2 points of inflection, and we should have we should have 1 max and 2 local minimums. Actually, one of these minimums is not going to be a local one. One's going to be like the actual minimum. Cool. Okay, so that's just another way that you can accurately get a picture of what a graph looks like. So for this one, all we did was find points of inflection and intervals of concavity. We didn't actually find maxes or mins or x or y intercepts or anything like that. So we didn't actually graph the function. This was just to show you how to use the second derivative to find points of inflection and to tell if a graph is concave up or concave down. Cool. The other way you can use the second derivative, I'll just talk about it really fast, sorry, because I know this is long. The other way you can use the second derivative is to classify your critical points as maxes or mins, which I kind of covered up here. So if the second derivative is greater than 0, then you have a local minimum. So like this here, second derivative is greater than 0, it's positive. So therefore it's concave up, so therefore we have a minimum value. Second derivative is less than 0, that means we have a maximum, concave down, and the second derivative is positive over here, so we have a minimum again. So you can also use the second derivative to tell if you have a max or a min at certain points. We don't know what those points are because we didn't actually find them, but that's how we could use the second derivative to tell if they're maximum or minimum values. All right, cool. And we might sum it up in another video, but that's it for now.